In this presentation, we will explore protection domains, which are fundamental to the security and stability of operating systems. The presentation is titled Protection Domains: Context for Privileged Execution in Operating Systems. We will define what protection domains are, examine their different types, and discuss how they are implemented. These domains establish secure boundaries for privileged execution. So, what exactly is a protection domain? A protection domain defines the set of resources that a process or thread can access, and the operations it can perform on those resources. Think of it as a virtual fence that limits what a piece of code can do. Here are some key points about protection domains. First, they define access rights and privileges. A protection domain determines what level of access a process has to system resources. Second, they isolate processes from each other. By placing processes in separate protection domains, the operating system prevents them from interfering with one another. Third, they enforce the principle of least privilege. Each process is given only the privileges it needs to perform its task, minimizing the potential damage from security vulnerabilities. Finally, they are fundamental to the operating system security model. Protection domains are a core component of how operating systems ensure security and stability. The visual on the right helps to illustrate this concept. It shows two circles representing user and kernel domains, with a protection boundary between them. Arrows indicate context switches between the domains, representing the controlled transition of execution between different privilege levels. There are several types of protection domains, each with its own level of privilege and access. Let us discuss three common types. First, we have the user domain. This is a restricted environment where applications run with limited privileges. It has limited access to hardware resources, cannot execute privileged instructions, has restricted memory access, and uses system calls to request services. Second, we have the kernel domain. This is a privileged environment where the operating system kernel operates. It has full access to hardware resources, can execute privileged instructions, has unrestricted memory access, and manages system resources. Third, we have the hypervisor domain. This is a virtualization layer that manages multiple operating system instances. It controls hardware access for virtual machines, isolates virtual machines, manages resource allocation, and provides hardware abstraction. Modern CPUs implement protection domains through privilege levels that control access to instructions and hardware resources. These privilege levels, often referred to as rings, provide a hierarchical approach to security. Each ring has a different level of access, with ring 0 having the most privilege and higher-numbered rings having progressively less. Here are some key points about privilege levels. First, they enforce separation between user and system code. Privilege levels prevent user applications from directly accessing or modifying critical system resources. Second, they prevent applications from executing privileged operations. User applications cannot execute instructions that could compromise system stability or security. Third, they enable secure system calls between domains. System calls provide a controlled interface for user applications to request services from the kernel. And finally, they are fundamental to the operating system security architecture. Privilege levels are a core component of how operating systems ensure security and stability. The visual on the right shows a diagram of the CPU privilege levels, with ring 0 at the center and ring 3 at the outermost layer. Each ring is labeled with its corresponding level of privilege and a brief description of its functions. System calls are the mechanism by which a user-level process can request services from the operating system kernel. This provides a secure and controlled way for user applications to access privileged resources. Here are some key points about system calls. First, they provide secure transition between privilege levels. System calls allow user processes to request kernel services in a controlled manner. Second, they validate parameters and permissions. The kernel verifies that the user process has the necessary permissions to perform the requested operation, and that the parameters passed are valid. Third, they prevent direct access to kernel resources. User processes cannot directly access kernel memory or other resources. They must use system calls to request access. Fourth, they are implemented via special CPU instructions. System calls are typically implemented using special CPU instructions that cause a trap or interrupt, which transfers control to the kernel. And lastly, they include examples such as the open, read, write, and fork functions. The visual on the right shows a code snippet demonstrating how a system call is made in Linux. The code shows a user space program calling the open, read, and close system calls to open, read from, and close a file. Context switching is the mechanism that allows the CPU to transition between different protection domains safely. It involves saving the state of the current process and loading the state of the next process to be executed. Here are some key points about context switching. First, it saves the current execution state. The operating system saves the current state of the process, including the CPU registers, program counter, and stack pointer. Second, it changes the privilege level. The operating system switches to the privilege level of the next process to be executed. Third, it loads a new execution context. The operating system loads the saved state of the next process to be executed. Fourth, it updates memory mappings. The operating system updates the memory mappings to reflect the memory space of the next process to be executed. Fifth, it preserves security boundaries. Context switching ensures that each process operates within its own protection domain. And lastly, it incurs performance overhead. Context switching can be a relatively expensive operation, as it involves saving and loading a significant amount of state. The visual on the right illustrates the process of context switching. It shows a user process A, a user process B, and the kernel. Arrows indicate the flow of control between the processes and the kernel during a context switch. Protection domains are implemented using a variety of hardware and software mechanisms. Let's discuss some of the key implementation mechanisms. First, memory protection. Memory protection provides hardware-enforced isolation of memory regions between processes and the kernel. It uses page tables to map virtual to physical addresses. It provides access control bits such as read, write, and execute, and it provides supervisor or user mode page attributes, as well as memory protection keys like Intel MPK. Second, privileged instructions. CPU instructions can only be executed in privileged mode to prevent unauthorized operations. Input and output operations are restricted to kernel mode. There are memory management operations, interrupt handling instructions, and CPU state control instructions. Third, hardware segmentation. It divides memory into segments with different access permissions and attributes. It includes code, data, and stack segments. Segment descriptors define boundaries. It performs privilege level checking on access and uses base and limit registers for bounds checking. And fourth, secure boot and trusted execution. These are advanced hardware features that provide isolated execution environments for sensitive operations. Examples include Intel SGX or Software Guard extensions, ARM Trust Zone technology, secure boot verification chain, and measured boot with TPM attestation. In summary, protection domains are a fundamental concept in operating system security. They provide a way to isolate processes and protect the system from malicious or faulty code. Let's review the key takeaways from this presentation. First, protection domains establish boundaries between different execution contexts to enforce security policies. Second, CPU privilege levels, rings, provide hardware-enforced separation between user and kernel code. Third, system calls enable secure transitions between protection domains. Fourth, context switching preserves security while allowing multitasking. Fifth, memory protection, privileged instructions, and hardware segmentation implement domain isolation. And lastly, modern systems extend protection with virtualization and trusted execution environments. The visual on the right summarizes the relationship between the different layers of a system, from user applications to hardware resources. The arrows indicate the flow of control between the layers, with system calls acting as the bridge between user applications and the kernel. If you are interested in learning more about protection domains, here are some references for further reading. They include Silbershots, Galvin, Gagné, Operating System Concepts, Intel Software Developer Manual, Protection Mechanisms, Salzer and Schroeder, The Protection of Information in Computer Systems. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.